All right, guys, welcome to this lesson on reaction types. We're going to look at several different types of reactions: combustion, decomposition. We're going to spend a lot of time on displacement and what are called redox reactions, so a lot of different ones. Some of you guys have seen this before. I got an email from a friend, and it says, most of the American population thinks it's improper to spank children. So I've tried other methods to control my kids when they have one of those moments. So my friend had difficulty working with his kids, so he tried his new strategy. He says, one that I found effective is for me to just take the child for a car ride and talk. Some say it's the vibration from the car, others say it's the time away from any distractions such as TV, video games, computer, iPod, etc. Either way, my kids usually calm down and stop misbehaving after our car ride together. He says, eye-to-eye contact helps a lot too. I've included a photo below of one of my sessions with my son in case you'd like to use the technique. And I was interested in this because, you know, I whack my kids, and then sometimes people say, you shouldn't be whacking your kids or whatever. So I kind of wanted to learn the technique he uses. So eye-to-eye contact helps a lot. It says after the car ride together, the kid usually calms down after a while and is compliant. So a little future when you guys become parents, hopefully not here soon. Reaction types. First one we're looking at, you guys, are what are called combination reactions, or they're also called synthesis reaction. It says two or more. I don't know if you guys can see in purple. I try to purplize the ones that I think you should probably write down. Two or more substances react to form one product. Here are several. I just had the first one, maybe just write down one so you have a representative type of reaction. For example, this shows magnesium reacts with oxygen to form magnesium oxide. And normally I would show that. You guys, if you would wait just a second, we will show that. One sec. A lot of you guys are already familiar. Sorry guys, I'm still here. Just wanted to grab some magnesium so you guys could see it. Those of you guys who had me before, you guys have seen this several times. So here I have just a piece of magnesium. We see a typical combination reaction. Magnesium reacts with oxygen. I'm going to get oxygen from the air. I just have to initiate the reaction. We usually initiate reactions with heat. Okay, and then here's the reaction. Don't want to set off the alarms. Okay, and so then it forms what we call magnesium oxide. See how it's combined together to form that compound. Okay. We also have what we call the decomposition reaction. That's where, rather than coming together to form a larger compound, larger compounds will break up into smaller compound the elements that make them up. So for an example, you might just write down one just as an example. For example, calcium carbonate. Got some, you guys, the calcium carbonate is really what your seashells are made out of, okay? And you can use a chemical process and separate the calcium from the carbon, and you can form calcium oxide and then carbon dioxide. But you guys see how two or more smaller substances come from a larger substance. And a lot of times you initiate decomposition reactions also with heat and you break it down. We have what are called combustion reactions. You guys, actually the one we just witnessed with the magnesium, that was also a combustion reaction or a combination synthesis reaction. But you often associate combustion with the flame. And you guys should know, and if we do have hydrocarbons, hydrocarbons are often combustible. And when we say it's combustion, we're saying it reacts with oxygen. So here would be a typical reaction. Here, you guys have seen this equation before. Methane, that's the gas we have in our Bunsen burners. It's combustible, it reacts with oxygen. And you guys remember what I was saying? Most hydrocarbons, when they react with oxygen, they're going to form carbon dioxide and water as a byproduct. But that would be a combustion reaction and you can tell when you have pure oxygen as a reactant. Okay? You guys, a lot of people are wondering, how do you tell what something is made up of? Well, just imagine they have a sample here. They'll put it into a furnace. So by a furnace, right, they're going to heat it up. They're going to pump oxygen into whatever the sample is. We want to know what it's made up of. Let's say it's made up of carbon, hydrogen, oxygen, but we don't know. Remember we were talking about the empirical formula. How do they figure out how much carbon there is, how much hydrogen and oxygen? Well, then they would put it through a series of steps here, and then they have the like a copper oxide. We're not going to talk about that. But then you'll have it pushed through, and it'll be in a vessel that absorbs water. Well, what they'll do is then they'll just weigh the water after the reaction, and then from that, knowing how much oxygen they put in, they can figure out how much hydrogen was in our original sample. Then that will continue to be perceived through a vessel that absorbs all the carbon dioxide that formed. Remember, these are the typical things that are formed in a combustion of a hydrocarbon. Then what they can do is weigh the carbon dioxide, and once again, knowing how much oxygen that they inputted, they can figure out how much carbon was in that original sample. And then obviously, to figure out how much oxygen was in that original sample, they would take the initial weight of the initial mass of the sample, and knowing the amount of hydrogen and the carbon, they can figure out how much oxygen was initially in that. So that's a typical way to figure out, and they call it analysis. We analyze it. That's why decomposition reactions are called analysis reactions, because we take a larger sample and we kind of break it down into its other components, lesser components. Okay, so, and then saying compounds containing other elements are analyzed using similar methods. So we'll just move on. It says, no thanks, I got to get into swimsuit shape before Shark Week. He's got Shark Week, and he wants to look good with ladies. Okay, oxidation reduction reactions. This is a new type of reaction for a lot of you guys. You guys want to write this down? What we mean by oxidation. Oxidation occurs when an atom or ion loses electrons. So if it loses electrons, it becomes oxidized. And reduction, as you might guess, is the opposite. That's when an atom or ion gains electrons. We'd say it's reduced. Okay? So in this case, this substance lost electrons, so this became oxidized, and this substance gained the electrons, so we'd say that substance became reduced. So write that down. Oxidation numbers. To determine an oxidation reduction reaction that's occurred, I'm going to show you guys how to do that. We assign an oxidation number. So you guys, I'm going to segue to a list rules here. If you guys would write down, the rules are going to come up here shortly. If you guys would write these down. So then you guys would pause it at this point, right? What I'm saying, free elements. Elements that are not in a compound are by definition assigned an oxidation number of 0. Simple ions, you guys are going to find oxidation numbers are kind of like valences. The oxidation number is similar to the charge you would expect it to have, or the valence. Remember our valence sheet. Oxygen usually is assigned a oxidation number of -2. You guys, that shouldn't be surprising, because you guys know it's 2 over from the right side of the right side of the periodic table, and you would expect it to gain 2 electrons, therefore acquire a -2 charge. It would also have a -2 valence oxidation number. Hydrogen, once again, this wouldn't be surprising. Hydrogen often has an oxidation number of +1. As you would expect, it's on the left side of the periodic table. It tends to lose 1 electron and acquire +1 charge, and thus have a +1 oxidation number. And just like with valences, the sum of the oxidation states must equal the total charge. Okay, so you guys should write that down. So, where we're going to use this, for example, we want to be able to identify whether or not a reaction is what we call an oxidation reduction reaction. In fact, we actually use a simpler term. We just call it redox, because it gets kind of annoying saying oxidation reduction all the time. We call it redox. And the reason why I want to know that, because you guys, all redox reactions can potentially be used for storage of energy, i.e. a battery. So, for example, let's look at one. I'll show you guys how you would identify. So let's look at a reaction that we had already done before. Magnesium reacts with oxygen to form magnesium oxide. Okay, so this is how you tell if it's a redox reaction. You first assign oxidation numbers to every atom. So, you guys, the oxidation number for magnesium is 0. You guys remember why it's 0? Because the rule says if it's a free element, it's not in a compound, it's 0. This is oxygen, that's pure oxygen. Once again, that's not in a compound, that's assigned an oxidation number of 0. Magnesium here, now it's in a compound. You guys remember, you guys look, it's in the second column, tends to lose 2 electrons. It's going to have a +2 oxidation number. And then you remember oxygen, it's 2 over from the right. And I'm looking at the periodic table. You guys should have a periodic table in front of you. If I went back and forth, it'd be more confusing. Oxygen has an oxidation number of -2. Now we look, and then we look at what happened to the oxidation number for each element. We look at magnesium, went from a 0 to a +2. What that means is magnesium lost electrons, it was oxidized. I put an OX. Now look at what happens to oxygen. If something gets oxidized, obviously if something lost electrons, another substance had to have gained the electrons. So it's obvious that the oxygen here, look, it went from a 0 to a -2. It gained 2 electrons. That means it was reduced. This is a redox reaction, and therefore it could potentially be used to power a battery. We're going to talk more about that second semester when we do electrochemistry. I'm not going to do more. Let's just do another one just in case you're a little confused. Let's say we have hydrochloric acid. Remember how I know it's an acid? It begins with a hydrogen. And let's say it reacts with sodium hydroxide. That's a base. Anytime you have a metal with a OH, that's a base. And what's going to happen is the hydrogen from the acid is going to combine with the OH from the base to form, you got it, water. That's what we call neutralizing, right? You get a harmful acid, a harmful base put together, you form harmless water. And then the 2 ions come together, the sodium ion and the chlorine ion. Okay? So that's ultimately what happens. So now I want to see, could I use this reaction to power a battery? Is this a redox reaction? What do? I assign oxidation numbers. Hydrogen +1. Chlorine -1. Remember, the sum of those will equal 0. Sodium here is +1. This one's a little, okay. You can remember oxygen's generally -2, and it should be that hydrogen is +1. Let's see if it works. +1 and +1 is a +2, and a -2. Overall, it's a 0. It looks good. Hydrogen here is a +1. Oxygen is a -2, right? 2 hydrogens +1, oxygen's -2. Sodium, and I'm going kind of fast, but I'm thinking this is a review for some of you because it's very similar to valences. And then, but remember, you assign it to every single atom, okay? And then chlorine here would be a -1. So then I look, do any of the oxidation numbers change? Hydrogen was a +1, it's a +1. Nothing happened, it didn't lose or gain electrons. Chlorine's a -1, chlorine's a -1, didn't lose or gain electrons. Sodium +1, +1, and oxygen -2, -2. None of the oxidation numbers changed. That is not a redox reaction. You cannot use that to power a battery. Okay, once again, we'll talk more about that second semester. Moving on. Here, you guys, it's called an activity series. This would be called the metal activity series, and it's kind of in order from the most active to the least active. And by active, we're talking about behaves like a metal. You guys remember what's characteristic of a metal? Metals tend to lose electrons. You guys, I can't stress that enough. They lose electrons. The ones here at the highest, the higher they are, the more likely they are to lose electrons. You guys notice, look, they're all metals, and it's showing them, right, it's showing they're all losing electrons, and then what happens to the metal? It acquires a positive charge. Well, you guys, it should not be surprising. What do you guys notice at the top? What are the most active metals? Lithium, potassium, sodium, all those. Guys, those are alkali metals on the far left of the periodic table. Check this out, barium, calcium, magnesium. Those are in the second most column, the alkaline earth metals. So it's not surprising that the most active metals, the ones that tend to lose electrons the easiest, the most likely to, are the ones further to the left. We knew that from our understanding of the periodic table. Now you guys look at the bottom. So the ones at the bottom, and you guys, this is all in reference to hydrogen. I'm not going to talk too much about that, but it's all reference to, in reference to hydrogen. You guys can see, look at all the metals under hydrogen. What do you guys notice about those? Guys, aren't a lot of those the kind of like your precious metals? Check it out, platinum, gold, silver. You guys, and why do we use platinum, gold, silver for jewelry? Why, guys? Because it doesn't corrode, right? You put on like a steel ring or something, it's going to start rusting, right? These are very unlikely to be oxidized, right? They don't go from their pure metal and lose electrons and thus react with other non-metals and so forth. Okay, so you guys should notice that. Okay, so this is an activity series. You guys, I think I put the activity series in the material section of Google Classroom. Let me know if I didn't, and then I'll have to upload that. Okay, so we're going to refer back. I'm going to show you guys how you could use this to make predictions. Okay, so last kind of reaction we're going to look at today is why am I still wearing those? Displacement reactions. Okay, and as you might think, displacement means one replaces another. So for example, this would be an example. So we get copper, and you guys see this here. So I'm putting copper, and what did I put copper in? Here's a solution. Hopefully you guys can see it. It's in a solution, it's really like silver nitrate, but let's say it's just the silver ions. So there's silver ions floating around there. You guys see how it's aqueous? and those are positive, and then they have some nitrate, NO3 minus, that stabilize it. So, but this is the reaction that's happening. So then we look at what's happening in the reaction. What happened? The copper went from an oxidation number, you guys remember, 0, and now all of a sudden it's what? Look, it's +2. What happened to the copper? It got oxidized. And you guys remember, if something gets oxidized, if it lost electrons, there must be something that gained electrons. And what oxidized this? Obviously the silver ions. Because look what happened to the silver ions. They went from a +1 to a 0. They obviously had to attract electrons. They got the electrons from the copper. It was reduced. And you guys see, this is what's happening on a microscopic scale, right? This is why chemistry can kind of be a little difficult, because you don't really, but you can kind of see what's happening here. Look, you put the copper wire, you guys know copper is an orangish brown metal, and then silver nitrate is actually just a clear solution. You can't still see those silver ions. But then you look at, over time, what you'll notice is you'll begin to see, I don't know if you guys can see it, a really shiny silvery substance. What's happening? Pure silver is coming out of the solution. So silver atoms are forming there. And then notice what's happening to the solution. I don't know if you guys can see, it's turning a faint blue. You guys remember what I said about blue solutions? Blue solutions tend to indicate there are copper ions. Copper ions make solutions blue. So that's what's happening. So you can kind of see the one displaced the other. Now the copper's going into solution and the silver's coming out of solution. That's why it's called a displacement reaction. Now you guys look, I don't know if you guys can see on this one. Now they're showing, look, it's slightly different. Here you had copper and Ag+, and here you have copper 2+ and Ag. And they're saying, will this occur? Will the copper ion be reduced to copper and the silver be oxidized? And I think you guys can tell by the X, that will not occur. And you guys should be able to ultimately, here in a few minutes, be able to predict why that would not have occurred based on your understanding of the activity series. I'm going to go back to it. So the question is, why does silver not oxidize copper? And it goes back to this. If we look at our activity series, you guys see, what is the more active metal? What's the one that's more likely to be oxidized, form a positive ion because it lost electron than the other? Because look, copper is higher on the activity series than silver. Therefore, silver will not oxidize copper. Silver will oxidize copper, but copper will not oxidize silver. You guys see what we're saying here? Look, see how copper, silver oxidized copper because copper got oxidized, but the reverse reaction, copper will not oxidize silver. That will not happen. Okay, you guys, I know that could be potentially confusing, but you guys, no one said AP chemistry is easy. That's why, you guys, a lot of this, I don't even necessarily expect you guys to get it the first time, or maybe even the second time, or maybe by the third or fourth time. That's why we do a lesson like this. I give you guys an assignment, you work on it, we talk about it in our live session, then you work on it again, and then I can talk to you individually, and then maybe by then it'll start clicking. That's just how it works. Okay, so I got a question for you. Okay, so I'm gonna go back to our activity series, so I'm gonna have it right here. So hopefully you guys do it, you guys actually try to do it, and maybe pause the videos to give you guys time to think about it. My question is, if I put zinc, okay, so let's say I have a solution here, okay? I have a solution in here of lead nitrate. So that's NO3 2, lead nitrate, okay? So you guys know, if it's a solution that's aqueous, you guys know what's gonna be in here. It's gonna be lead ions, and it's gonna be nitrate ions, right? You guys remember they separate? Okay, so now, question is, I'm gonna put zinc in here. Let's put zinc in there. Question is, will I expect a reaction? You know, so basically, when I put a chunk of zinc, let's say I put a chunk of zinc in there, will the chunk of zinc just fall to the bottom and no reaction? Or will there be a reaction? The key is you have to look at your activity series. So I'm gonna give you guys a sec, so you guys pause it if you can. Well, we look here, so what do we wanna do? We have this metal zinc and we have this lead, which is already oxidized, right? It's already lost some electrons. The question is, will this oxidize this? So I look on my activity series. I look at zinc, and I look at lead, which is the more active metal? Zinc. Zinc is more likely to be oxidized than lead. So what will happen? The answer to that is yes. There will be a reaction. What's going to happen is zinc will be put into this solution with lead ions, and what's going to happen is, because the zinc is more inclined to be oxidized, the zinc will become oxidized, and what's going to happen? The lead will become reduced. So yes, there will be a reaction. Okay, let's do another one. What if we have the same solution? Let's say if we had copper. So I put copper in there. Will there be a reaction, yes or no? So pause it, give yourself some time to think how we would determine that. We look at where copper is, and we look at where lead is. Which is the more active metal? Lead. Lead is more likely to be oxidized than copper. Well, if lead is already oxidized, now if I put copper in here and lead's already oxidized, nothing's going to happen. What's going to happen is the copper is just going to fall here to the bottom, and it's just going to stay as pure copper. Okay? And we're going to do one. Oh, and this would explain why. You guys think about it. We used to have, I don't know if you guys know what we used to have our pipes made out of, you know, like our water pipes. It used to be lead pipes. Now, one of the reasons why we don't have lead pipes is because lead is pretty toxic, and you can, I don't know if you guys heard about the whole Flint, Michigan thing, and they had toxic from lead from the river and stuff. But anyways, it can do some serious damage. But you guys can tell, what do we use primarily for water pipes now? You guessed it, copper. We use copper pipes. Why? You guys will notice because copper is less likely to be oxidized. You guys, a good word for oxidized, more familiar with, maybe rust, right? Copper is less likely to rust. And when we say rust, we're talking about react with oxygen in the air, because oxygen is what takes the electrons from these metals, right? Copper is less likely, therefore copper is going to last a lot. It's going to have more integrity than your lead pipes. Okay, last one. What if we did iron? So let's say I put a chunk of iron in there. Would a reaction happen? Okay, well, let's look at it. So I got my iron, and where you could have potential displacement is with the other metal, right? Well, I look here and I look for iron, and I compare that to lead, and we see which one is more active. Iron. Iron is more likely to be oxidized. So what will that happen? It will indeed happen. Iron will be oxidized. It'll go from Fe, pure iron, to iron ions, and lead will be reduced from a +2 to a pure lead metal. And you guys, this would explain too why, oh, this is something too. You guys, think about it. We used to even use, in fact, in my home, like a sewer line used to be out of iron, right? They used to just use iron pipes, and iron's good because it's strong, but you guys already know what's the problem with iron. Iron can tend to be easily oxidized. So you know what they do now? You guys know steel is primarily, it's an alloy that's primarily iron. What they do now is they take your steel, because you still want the strength of steel, right? You don't want your pipes breaking easy. But to reduce or minimize the likelihood that's going to rust, they galvanize it. I don't know if you guys have heard of that word, galvanized steel. You know what they do with it? With that steel, which is primarily iron, they coat it in zinc. So they just put a zinc coat. And why would they do that? Because you guys think about it, when it's exposed to oxygen, what's oxygen going to oxidize first? The zinc or the iron? It's going to oxidize the zinc. Zinc is more active, it's more likely to lose its electrons to oxygen. So the zinc becomes oxidized, and then it forms like a zinc oxide coat on the outside, protecting the iron, which is really strong, from any potential oxidation. All right, guys, so that's it for today. Hopefully you guys have enough to at least help you on the assignment that you're given. All right, guys, bye.